All right. We're still missing 6 people, so hopefully some of them will show up. Okay. Now, so I see that submissions of homework 2 are beginning to trickle in. The operative word being trickle. So hope to see more of those before the end of the day. Okay. Now, one thing we'll talk about, since all of you are going to be, well, unless you're graduating, going to be choosing your classes for next semester. So I just want to mention that as my obligation to do shameless plugs for any of my classes. So so here's the scoop, just a summary of what the deal is with 461. Okay, so first, in terms of degree requirements, counts as elective like 460 does. Well, 460 serves dual purpose, elective or the technology requirements if you did not take Math 305. Also, this is something that I think hasn't really been discussed in the bulletin. About what's referred to as a second course. Because if you look in the bulletin under now, of course, if you're not in the Math BS program, this doesn't apply to you, but for most of you it does. We have in the bulletin, it says group 1, 2, and 3, and you take one elective from each, and that sort of thing. But we haven't really regularly offered anything from group 3. So some time ago, the faculty voted to instead require that as long as one of the courses you take is a second course within a particular area, then your mix of electives is deemed sufficient. Now, there are several courses that satisfy this requirement. For example, Math 420 is Prob and Stats 2. Not required for BS majors, it is required for licensure. So that fulfills the second course requirement also. Okay. And as far as offering frequency, now 460 is, we offer it every fall. With a different instructor. 461, we try to offer it every fall. It technically goes in the schedule. Historically, every other spring is when it actually runs. The other years, it tends not to make. Okay, so in other words, for you guys, the boat comes around once. Okay, topics. So numerical methods for the one thing that was meant to be covered this semester, but due to basically hitting a reset button in this class, got pushed to next semester for nonlinear equations. So in other words, root finding. And then courses that are always covered in 461, differential equations. So initial value problems, like in Math 285. So numerical methods for those equations. Also boundary value problems. So second order ODEs, where you have boundary conditions instead of initial conditions. And also systems of linear equations. Like in 326, except the methods, some of the methods are very similar, row operations, Gaussian elimination, that sort of thing. But also iterative methods that are much more useful for large-scale problems. So there's a lot of focus on iterative methods that isn't really focused in 460 is a major theme in 461. As far as the intended audience, generally, however many students take 460, it's like about roughly half or so that move on to 461. But if, okay, so I will say my last comment on this, highly recommended for if you are or might be active in undergrad research, or I know some of you are in this class for that very reason anyway, or any like advanced like graduate study. If you're in that demographic, which I know only a minority of you are, but 461 is strongly recommended because as the purpose that brought you to 460 really gets fulfilled in 461. So think about that if this applies to you. Okay, so that's the end of my shameless plug, and I hope to see at least some of you next semester. Okay. Well, also, how I'm running things now toward the end, now that I've settled on a pattern here, is what will apply in 461, so it won't be so chaotic. And the other thing I want to, also the textbook will be finished because I have to. It's due at the publisher January 15th. So, and you still find mistakes, point them out to me because that goes into the second edition. But I won't be scrambling to finish it like I am now. So I hope you all enjoyed your fall break, or should I say, time away from classes to catch up on stuff that you fell behind on. And that applied to me just as much as you. Okay. Now, do we have any homework 2 questions? I should say last question, since now it's time to finish that up. Oh, well, okay. Oh, I'm going to see 19 more sparkling submissions. Okay. As a reminder, I know several of you turned in something before. If you are updating that submission, because that was some time ago, again, the preference is to just go ahead and resubmit the whole thing. That way I'm not having to go across several emails to figure out what is the thing I'm supposed to look at, grading-wise. Okay, so we're all putting homework 2 behind us. All right. Now, are there any questions so far? I mean, the focus for today, as far as what I'm covering, is section 6.3. In case you didn't get any notification, I put the quiz out on 6.3, the concept check questions, and I want to let you know about. And I just added a new question on the questions page. Again, be sure to check the questions page in case your question is already answered there. So as far as how I'm handling deadlines for the quizzes, I want to have a nice, easy to identify pattern for that. So I'm using these dates that you see for setting the due dates for the quizzes. The only difference is it's shifted by 1. So for example, the section 6.2, I recommend you finishing at by the 31st. That means I want you to have a quiz for that done by the 27th. And as you recall, the quizzes for section 6.1 and 6.2 were lumped together. 6.3, I recommend finishing the problems on this section, which includes the explorations, by Friday, November 3rd. Therefore, I've set the due date for the quiz to be October 31st. So if there's going to be this kind of spacing between for all the quizzes for all the sections. So I've only put out up to 6.3. I'll put out these next 2 shortly, but you have plenty of time to do those. So in other words, when I put out 6.4, that's due November 3rd. When I put out 6.5, that'll be due November 7th. Oop, I lost a parenthesis there. Okay. Now, in several cases, like I think a lot of the scores that I gave for 6.1, 6.2 was 7 out of 8 points. So by all means, try to get that last point. You can submit as many times as you want. Okay. So are there any questions on homework 3 up to this point? You're a really sedate bunch today. Okay. So, well, as long as you enjoyed it, then. Okay.
On the concept check for 6.3.
Yeah.
Number 4, I guess I don't really get what class.
Okay.
I think I do, but I just don't.
Okay, number 4. Okay. It's probably out of date. Whoops. Dang it. Oh, okay, this question right here. One of the theorems in this section gives the answer to that. All right, any other? Homework 3? Not started yet? Okay. All right. Now, so what I'm going to do, while we're in this section, so what I'm going to do as I cover each section is, the focus is going to be on what is it going to take to enable you guys to work out the explorations that I've assigned in this section. Now, there are 9, there are double-digit explorations, 12 explorations in this section, but I've only assigned 3 of them. Trying to be a little merciful anyway. Numbers, so this one, 6, 8, and 9, and they all involve coding. So what I'm going to do is, well, first I'm going to give a summary of what is going on with these explorations, and then I'm going to step through an example in MATLAB that what I'm hoping will accomplish 2 things, and that is help cement the concept that's covered in this section of Newton interpolation, and also put you on the path to be able to not only work these things out on paper, but like on a final exam, but also in code. Okay. So first, a little bit of commentary on the explorations from this section. Okay, so, whoops, 6, 8, and 9. So you're writing a function. So these are all. So the goal of all 3 of these, and the reason why I assigned these 3 in particular, is to develop a MATLAB program for computing the interpolating polynomial Pn of x using Newton interpolation. So that's what's going on under the hood. Internally, it's going to be using Newton interpolation instead of Lagrange. But the usage is similar to polyfit So the way polyfit works is you have an output P, and your inputs are a vector of x values, vector of y values, and a degree. Okay. Am I in math mode? That's kind of weird. Okay. Sorry, something screwy is going on here. Because I don't want this to be italics. Okay. For some reason it thinks I'm in math mode, and really I'm not. Okay. Okay, much better. So this computes the coefficients in power form of polynomial of degree n that fits the points in the vectors x and y. Now, what polyfit does is, regardless of how many points you have in x and y, generally n plus 1, it lets you pick whatever degree you want. Now, we don't actually need or want that kind of flexibility, because if you specify a different degree, it's going to use some other technique that we're not covering. So we're not going to bother with that. So for our purposes, n is always the length of x minus 1. So if you assume that you have n plus 1 points specified in x and y, and then so then the degree will just be 1 less than that number of points. So that'll simplify things for us a little bit. Now, okay. So, and the coefficients are ordered from highest degree to lowest. Just like, so this is how polynomials are always represented in MATLAB. So the idea is we're creating a function that has a similar usage. You specify x, you specify y, you get out, and we don't need the degree, we know what it is, and then we get the coefficients in power form of our polynomial. So you could use, instead of using polyfit, you can use your own function. That's really what's happening in both of these courses, is you finish a course, if you do all the explorations, with your own collection of MATLAB functions that you're free to mess with for implementing numerical methods. It's like you're building your own software library in a way. So this task of building this kind of function yourself is broken down into 3 stages in these 3 explorations. So the first one is, okay, so 636. We have this function. I'll write it out again here. I just need to refresh my memory as to what it was. So this completes a divided difference table from the given points, the x and y values. Okay. So the divide difference coefficients. So C is the output. It contains the coefficients of your interpolating polynomial in Newton form. And I'm going to review all this when I step through an example. But so the point is, so what happens is you're going to have like a constant term plus another coefficient times x minus x naught plus another times x minus x naught, x minus x1, and so on. And I'll show you that. But that's not really the form that we want. So that's why we go to the next exploration, where you write it. And that, now I should mention, what you're doing is the pseudocode for this is already given in the textbook, algorithm 634. So your job in this exploration 636 is to take this algorithm translate that pseudocode into actual MATLAB code to perform this task. Okay, and I'll talk more about how you actually go about it. If you have a description of a algorithm in pseudocode, what do you have to do to get actual MATLAB code out of that? Okay, and the next exploration, 638, is the second stage of this task. And you're writing another function. PowerForm is its name. And so what this does is it converts Newton form coefficients that are given in the vector C. So in other words, the output of diff-diffs, of the output from your divided difference table, goes as input to the next function, PowerForm, to a PowerForm that's stored in the vector P using the centers stored in X. Because the Newton form has two aspects to it. There's the divided differences that are the coefficients, but also you have the centers, because you have all these linear factors of a form x minus x naught, x minus x1, etc. So those centers are specified in the vector x. So, and this, I don't give pseudocode for the whole thing, but it uses algorithm 636, which is called nested multiplication in a loop. So this algorithm, you should write a separate function for nested multiplication. And then you can just call that function, and that makes this job a whole lot easier. And then finally, the last piece of the puzzle, is 639, is Newton fit, and that takes as input x and y. So in this one, there's very little to do. Literally, the function is 2 lines long, aside from the leading line. So it's 3 lines total. Because you'll take x, y, you'll call diff-diffs. You'll get out the PowerForm coefficients. Pass that to PowerForm. That converts to PowerForm and gives you output P. That is the output of Newton fit. So it's totally passing the buck to these two. So I want to emphasize the overall task, okay, that's pretty substantial. But each piece of it is not. So if you look at the algorithms that need to be implemented, so really there's going to be 4 functions altogether. These 3 right here, and then for 638, you really should write a separate function for nested multiplication. That's not a very long function either. So you have 4 relatively small pieces put together to perform a larger task. And that's what programming is. Because we take these challenging, daunting tasks and break them down into manageable pieces. And then we just had to figure out how to put them together. Okay, so this is your blueprint of a path that you're going to follow to do all the explorations that are assigned for this section. So what I'm going to do, and I guess you could say that this is one benefit to you not really having questions today, and that I have more time to do this. I'm going to step through an example where I'm going to show you how interpolation, this Newton interpolation, is carried out as if you were to do it on paper, but I'm going to do it in code, and basically have this evolve to the kind of code that you need to produce. So it's almost like a watered-down version of what you're going to be doing. Okay, and need to queue up my cheat sheet here. So first I'm going to type in here, here's what the example is going to be. All right, so find second degree polynomial P2 of x that fits this data. So my x values are equal to 1, 2, 3. And then my y values that go with them are equal to 1, 8 and 27. What's the pattern in those y values? Yeah, for perfect cubes. So, in other words, what I'm doing is find a quadratic interpolant of x cubed. So because my interpolant is only of degree 2, it's too low a degree, it's not going to get x cubed exactly. It's going to match at those 3 points. And once I produced it, I go ahead and plot it for you so you can see what kind of a match it is. Okay. But at least this way a lot of the numbers work out pretty nicely. But we're going to do this using Newton interpolation. And once we have this in Newton form, then we need to convert to power form. So in other words, so to refresh your memory, Newton form. Oh, dang, it's gone to another page. Okay, so Newton form is going to be this form. C0 plus C1 x minus x naught plus C2 x minus x naught x minus x1. So that's what the divide difference table will give us. And then power form, same polynomial, but in our form we're accustomed to. Okay. So in other words, exploration 636 is meant to produce this first form from the values of x and y that you're given. And then exploration 638 is meant to take something that's already in this form and convert it to this form. And then 639, you just put those two pieces together. Okay. It's putting up these extraneous spaces. It's driving me nuts. Okay. All right. So now what I'll do is, okay. Actually, I'm going to put this. No, stop that. Dang thing. Put that onto a separate page. Okay. All right. So any questions about the intent of the example here before I really get into it? Okay. So, I'm going to create a script where I'm going to work out the whole process of figuring out this second degree interpolation. But I'm going to do this in a way that's analogous to if you were to work this out on paper. If I just gave you, here are the x values, here are the y values, figure it out, do a divided difference table, then that's what I'm going to type in here. But I'm just going to have MATLAB carry out the actual arithmetic. Because I don't trust myself to do that anyway, especially in the middle of class. Now, so what I'm going to do is I'm just going to make up variables for all the things I need. I'm not going to think in terms of data structures or anything like that because we're still in this working it out on paper mode. Because I figure that's your most comfortable starting point, and then we'll progress to actual code, which, as you'll see, will look very different. So I'm going to specify my x values and my y values. Actually, I'm going to make this, I want to fit more on one screen, so I can put multiple statements on a line. So this is just what I typed in to the LaTeX notes earlier. Okay, so here's my my given data. Okay. So now, I'm ready to do my divided difference table. Now, there are going to be 6 entries in this divided difference table, and I'm going to write out in comments first the notation from like from a book, for instance, or other books about what that notation looks like. So we have f square brackets x0, f square brackets x1, f square brackets x2, and these are just the y values. But then I compute from that, from fx0 and fx1, I get x0 comma x1. So first column, 0 order divided differences. Second column, actually I'll put this up top. Second column is order 1 divided differences. So these two are used to compute fx1, x2. And then order 2 divided differences, fx0, x1, x2. So these are computed using, so each divided difference is computed using the 2 to its left. What was that? Oh. Ah, okay. Glad you could join us. What? Oh. Okay. Oh. Okay. Well, at least I'll have a video for what was missed. All right. Now, so each one's computed using the 2 values to its left, and I also list the x values. Okay, which would be x0, x1, x2. Okay. All right. So for instance, fx0, x1 is computed using this minus this divided by this minus this. So that's your divided difference table. So now I'm just going to carry out those exact computations in here. Bless you. And my variable names, I'm just going to use these, except I'm not allowed to use square brackets in a variable name. So I have to, or commas for that matter, so I have to leave those out. But otherwise, they'll match exactly. So for instance, 0 order divided differences, I'm just going to assign the y values. So fx0 is y0, fx1 is y1, fx2 is y2. Okay. Now for order 1, I have 2 of these to compute, these 2 right here. So like fx0, x1 would be these 2 subtracted, fx1 minus fx0, divided by x1 minus x0. So the corresponding x values. Bless you. The next one is this one, which I'll call f x1, x2. So what should I put here? Similar idea. That each divided difference is computed using the values to its left. It just follows the same pattern. Uh-huh. Yeah. Okay. So now these 2 divided differences of order 1 are complete. And now I have 1 divided difference of order 2, this one. So I'm going to call that f x0, x1, x2. And again, you're using the 2 divided differences to its left. And also remember, to find out which x values you use, like you're going to use these 2 for your numerator, and then you're going to, yeah.
There's trouble with this class connecting.
Oh, I guess down at the other end there was some trouble. Yeah, but we're connected now.
So, is this the one that connects to the 2 other campuses?
Right. Yeah, we're both here. Yeah, we're connected now. Right. So, to get the x values you need, you start here and you go back, upward diagonally, and then to the left to get the next value, and then down diagonally also to get the other x value. So who can tell me? I'm going to have, again, a divided differences, something minus something else divided by something minus something else. So what would I put in here to complete the divided difference table using a variable names that I already have? Yeah, fx1, x2 minus fx0, x1, okay. Divided by what? x2 minus, yes, x0. Okay. Any questions about how the divided difference table is obtained? So again, use the two values to your left. Go back, upward and then downward to see which x values you're supposed to use in your denominator. Okay, so now the Newton form, if I were to write it out, would be P2 of x is equal to, now you go down the top row. So fx0 is a constant term, and then fx0 x1 times x minus x0 plus f x0, x1, x2 times x minus x0, x minus x1. So, if all we cared about was the Newton form, we would stop here. But we want power form. So what I'm going to do is, for brevity, I'm going to label these coefficients C0, C1, C2 for what I'm going to do next. And notice the pattern in the divided differences that you take. So notice, like we have x0, then x0, x1, then x0, x1, x2, or it's those divided differences. These other divided differences we're not using, but we still needed them to compute the ones that we are using. So that's why we need to compute the whole table. Okay, so now we have these coefficients. We need to convert to power form using nested multiplication. Now, I'm going to put up the algorithm for nested multiplication. Okay, here it is. So what we have here is, as your input, you have your divided differences, your Newton form coefficients. That's why I call them C0, C1, and C2. They're labeled the same way in this algorithm. And then you have your interpolation points, x0 to xn. Those are playing the roles of your centers. That's how we refer to them here. And now nested multiplication is used to evaluate the polynomial at a given x. But it serves another purpose, and that is these new values that it computes, the b's, those are the coefficients in a new form where the value you plug in, your x, is the first center, and then the other centers are shifted down. So what I'm going to do is I'm going to use x equals 0 in this algorithm because I want all the centers to be 0. That's what power form is. So I'm going to run this algorithm with n equal 2, and what I need to do is run it twice. So whatever the degree of your polynomial is, that's how many times you need to use nested multiplication, because the idea is you have n centers. You're shoving all those centers out, and you're replacing them with zeros, and you only get to replace one at a time. So that's why I need to use this twice. So okay, so my original coefficients are C0, C1, C2. My original centers are x0, which is equal to 1 in this case, and x1, which is equal to 2. Okay, I'm going to use nested multiplication with x equals 0. So if I follow this algorithm, okay, actually what I'm going to try to do is I want to, if possible, have both on my screen at the same time. Oh, okay, that works. I can make this a bit smaller. Okay, actually make it a little bigger. Okay, so it's this algorithm, but I'm going to do it not as a loop. I'm just going to write out the statements. So B2 is C2 because n is equal to 2. And then in a loop, I have I going from 2 minus 1 down to 0. So 1 to 0. In other words, it's going to run twice. B1, so I equals 1 at the start, is equal to C1 plus x is equal to 0. I'll just fill that in here. So 0 minus x1 times b2. And then I do this again for I equals 0. B0 is equal to C0 plus 0 minus x0 times B1. This last statement I don't need because I don't really care about evaluating a polynomial. I just want to change it. So does anyone have any questions about how this statement inside the for loop got translated to these two statements out here? All I'm doing is I'm just running what's actually in the loop. Right. And keeping in mind that in this example, n is equal to 2. So now the new coefficients, B0, B1, and B2, the new centers are effectively shifted. 0 and then x0, which is equal to 1. So this one, the 2, fell off the edge. It's gone. So the new, whoops. Therefore, the new form is equal to P2 of x is now B0 plus B1 times x minus 0, because that's the new center, plus B2 times x minus 0, x minus 1. So if I simplify this, so x minus 0 is just x, and this is x. It's on the way to power form. We just need to do this one more time. So with nested multiplication, I'll call these coefficients A0, A1, and A2. So A2 is B2. So I'm going to do the exact same thing as up here, except, oh, actually, what I'm going to do is I'm going to change my centers. So x1 is equal to x0, x0 is equal to 0. So those are the new centers that I have. That way, I can just keep using this, and it'll be correct. So I'll have B1. So now, here I changed C's to B's. Now B's become A's. All right, so plus 0 minus x1 times A2, and then A0 is equal to B0 plus 0 minus x times A1. Okay, and now we're done. We have our power form coefficients. So A0, A1, A2 are our coefficients. The new centers are 0 and 0. And actually, I'll go ahead and so this will have the effect of setting both of these equal to 0, both centers equal to 0. And our new form is equal to A0 bless you, plus A1x plus A2 times x squared. And this is power form. So that's the whole process. This is like if you were carrying this out on paper just using a calculator, these statements that I typed here, for most part, maybe simplified, but this is exactly what you would do. And now I have this in code, except there's some limitations. For one thing, what I've typed in here will only work on degree 2. I can change the x and y values if I want, but I'm limited to second degree. You want, in your explorations, you want this to work for any degree. Also, there are situations where I could have used loops or maybe used fewer variables. So that is not taken into account here either. But I'm going to run this in a moment. Well, what I want is I'm going to store these coefficients in this row vector P, A2, A1, A0, and I want to print them out because those are this is how MATLAB represents polynomials in power form with the highest degree coefficient first. Okay. All right. So, and I know what the coefficients are supposed to be, so then I can tell if I actually did this right. Okay. So, any questions about what happened here? Divided difference table or nested multiplication before I run this thing. Of course, I have my cheat sheet here, so if this doesn't work, it's going to be pretty embarrassing. But that's the risk of teaching. Okay, so I'm just going to run this, interp2 demo. Watch there be an error or something. Oh, wow, it worked. I'm seriously surprised. Because I've told you what happens to my IQ during class. So P2 of x is equal to 6x squared minus 11x plus 6. So that is a polynomial that agrees with x cubed at x equals 1, 2, and 3. But only those points. So what I'm going to do is I'm going to plot this. So first, I want a whole bunch of x values, like between 0 and 4, let's say. And then okay. I'm getting quiz submissions during class, which is interesting, but as long as you're also paying attention to what's happening during class. All right, so my y values, well, I'm going to plot the x values, and then my function I'm interpolating, x cubed. I'll do that in blue. Okay, so this function I'm trying to fit. Let's make it a little bigger, or a lot bigger. And then I'm going to take my polynomial, P, plug those same x values into it, and plot that in red. And we see that there's agreement in here, not so much when you're further away. And I'm also going to show the actual interpolation points that I'm fitting. X equals 1, 2, and 3. So y values are 1, 2, and 3 cubed. And I use dot cube because this is a vector. And I'll plot those using black circles. Okay. So now you can see here at the black circles where my blue cubic function and my red quadratic function agree with each other. And in between, there's a decent agreement. But once you go past x equals 3 or in this direction or past x equals 1 in this direction, then they don't really agree anymore. So I want to point out that what's happening in here, x equals 1, 2, and 3, and in between, well, that's interpolation. So interpolation is when you're fitting a function at certain points and you're evaluating your approximation to points in between the points that you're fitting. Whereas out here, past x equals 3 or past x equals 1 over here, that is not really interpolation. That's extrapolation. Extrapolation tends to be horribly inaccurate to compare to interpolation. It's generally not a good idea. Although when I get to differentiation, or actually certain forms of integration, we will see that there are cases where extrapolation can be very helpful, but this isn't one of those cases. So with polynomial interpolation, you want to ideally use it really for interpolation, not extrapolation. Like if you think of your x value is really referring to time, it's good for like contemporaneous data, but not predicting a future or fitting the past. Okay. All right. Now, if we go back to this code that produces divided differences and also converting to power form using nested multiplication, this is not really like the code that you're going to write, because your code is meant to work with whatever degree that you're given. And so what I'm going to do during the rest of the time is modify this code to get closer to that objective. And this will help you get started on your coding tasks for this section. Okay. So for one thing, we have so much similarity between these statements and these statements. So what I'm going to do is, because we don't want to have redundant code like that. Ideally, we should have a function that performs this task, and we call that function twice. Because what if there's some discrepancy between these? When you have redundant code, that invites mistakes, where you have statements that are very similar, but they really should be performing the identical task, and maybe you made a mistake in one of them. So what I'm going to do is I'm going to create a new function. I'll call it nested mult 2, but 2 is for the fact that this is still hardwired to do quadratic. And what I'm going to do is I'm going to cut these statements. Oh, these should have been x. I mean, x is 0, but for generality, it should be x. So I'm going to cut these statements from here and put them in here. And then I'm going to make this a function. Now, in the square brackets go my outputs. In the parentheses go my inputs. So, of all the variables that we have here, what ones are inputs and which are outputs? Some are both, actually. But so what is given that I should put in here in the parentheses? As opposed to what is produced, that should go into square brackets. What? Well, x0 and x1, which go together, they're actually both. Because they come in as given and used here, but then they're also modified. So I'll put them in a list. I'll put them in both lists. But then everything else in here is playing a role as either only an input or only an output. All right, we have quite a few variables to choose from. So what is given as opposed to what is produced? We call it either one. Don't be shy. The B's, B0, B1, B2, input or output? What? Yes. Okay. And these are the most important outputs. I'm going to put them first. Okay. What else do we have that I've not yet classified? What are they? They are input. Yeah, because they're used. They're not modified. Good guideline. Is it on the left or right side of an equal sign? If it's on the left side, then that would be like an output. That's a result. If it appears only on the right side, that's an input. There's one item left. Which is it? One variable. Yeah. What is it? Input or output? It's an input. Yeah, because it only appears over here. It's only used. It's never modified. Okay. All right. So now I have a function that carries out this nested multiplication. So now I'm going to replace those two instances of nested multiplication back here So this carries out that job. And then I want to do it again over here. I'm going to get rid of these statements. Well, first I'll comment them out. I'm not going to use them anymore. And then I'll get rid of them momentarily. So I just need to adjust the parameters. So what needs to change in my list of inputs, list of outputs? I still want to carry this out. But some of these parameters, input or output, need to change and some don't. What needs to be changed? Yeah, A1 okay, as input or output. Their output. Okay, how do I need to change the input? B's. Yeah, so before the C's were used to convert to B's. The B's that were output before are input now. Okay, so now I can get rid of these statements. Nice to have a code made a little shorter. Okay, so now, so now I actually, well, one thing I should do after I make a change like this, need to make sure my code still works. So I'm gonna run it again. Okay, it still works. That's a relief. Never know. All kinds of opportunities for things to go wrong. Okay. Now, a further change I'd like to make is this is still hardwired for second degree interpolation. We have 3 coefficients going in or coming out. Also, this function also hardwired only for second degree. It only goes through this these statements twice. Now, if I want to be able to adapt this to any degree, the problem is, look how I've described these coefficients, C0, C1, C2. Now, if I have a higher degree, then of course I'll have more coefficients. And I don't want to have like many versions of this function. I want to have one function that does it no matter what the degree is. So instead of using this, like these kind of coefficients, C0, C1, C2, can anyone tell me what I should do? What should I do instead? How I should represent the coefficients that I have, however many of them I have. What should I do that handles the general case? What kind of variable should I use? It's a vector or an array. Yeah, well, they're one and the same in this case. Yeah, so what if at the start, instead of doing this, I have my divided differences. I'll make a vector, I'll call it C, where I store my coefficients. And now I have a vector C, and my centers, I'll call it XC, the centers are X values. And I'll make that a vector also. And then X is still a scalar. And then similarly, I'll have a vector that's output, B. And then the vector centers. And then I can make the same change down here. So now my interface is greatly simplified. Even though the computational task that's being performed is exactly the same. And now, in fact, I don't even need A and P both anymore. My output is just P, so I don't need this statement anymore. So if I switch to using vectors, now the code becomes a whole lot simpler. But now what I want to do is I need to go back here and make the similar changes over here. So this will be a vector B, and this will be a vector C, and then my vector of centers. Okay. Now, where things get more interesting is, now I need to make these changes over here because I'm going to be accessing elements of these vectors or arrays. So instead of saying B2 equals C2, really what I want to do is I want to take the like the last element set the last element of B equal to the last element of C, because we're going from like this vector B corresponds to the vector B0, B1, B2, and similar for C. So just show the correspondence between the old variables and the new for purpose of translating this. So, so the thing is, we need the length. N, the degree we're dealing with, would be the length of, well, which vector? And so N should be the degree. And up to this point, it has been 2. So the length of what vector gives me the degree in any case? xc. Because we have 2 centers in this example. So, all right. So now we have N. Okay. Now here we have the last element. So I could say B end is equal to C end. So that assigns the last element of C to the last element of B. Now we have this loop. This should be done as a for loop. Now, what should be my values here? What should I put here? What am I counting from what to what? So before n is equal to 2, it has to be done in terms of n generally. So what values should I have I iterate over? Well, actually, the answer is already on the screen, but the idea is you look at how I was counting before. Look how I was indexing before. In terms of these formulas. Take a stab. What? I'm sorry, I really cannot hear you. Well, yeah, so n, yeah, okay, okay. So like that's your starting value. Well, there's a total of n iterations. But should it count forwards, backwards? So look at the indices that are used before. These statements give you an idea. Because the idea is you want to rewrite these expressions to condense it to only one statement involving I to help you count from whatever to whatever. So are we going forwards or backwards based on these 2 statements? Yes. So for instance, we can start at n, and it needs to run n times. We have 2 statements here, so in general it'll be n statements. So it'll be n counting down to 1. Okay. So now I can change this to be, instead of b1, be bi is equal to ci plus x minus xi. And then what should I put here? I plus 1. And that's going to be fine because the vectors b and c have length n plus 1. So this will be a valid index. This statement is gone. So now this statement, so this part is complete. The only thing left is we have to do something similar to the centers. So can anyone tell me, in place of these 2 statements that I'm commenting out, we need another loop that deals with this. So can anyone tell me? So we have x, c, is a vector of length n. And we need to do these kind of this kind of assignment. Now, the first center will be 0, or actually it'll be x. Whatever value came in is what will go here. So I'll handle that part for you. Actually, it's xc is equal to x. So what should I put here? Again, it should model what's going on in the statements that you're replacing, because you're trying to get it to perform the same task. So what should I put here? I, counting backwards or forwards. Again, it comes from these statements. What? Yes, backwards. So we'll just make I count from n down to 1 again. Oh, actually, this statement is already covered. So count from n down to 2. Okay. All right. Let's see. So based on this statement, what should I put here to complete it? So, because what's happening? I'm assigning one element of this vector to a different element. Yes, x of I equals what? So it's equivalent to this. I minus 1. Yeah, yes. So it keeps shifting all of them up. The last iteration, xc2 will be xc1. So these are all valid array references. And then xc1 gets overwritten with a value of x that's passed in. All right, and this function is done. So now I get rid of the statements that I don't need anymore. Okay. Actually, what I'll do when I post this, I'm going to post the original version and this version. I'll have the original version commented out so that you can see both. It's important for you to understand, because the thing is, how I wrote it before is based on the kind of formulas you see written in textbooks, not just mine, anybody's. And that's what has to be translated into code. Now, at least some of the pseudocode in the book, and books in general, have for loops in them. But to make it leap from how you work things out on paper to how you work things out in code. So now you see some of the steps that are taken, and this is actually why it's quite difficult for someone, even though they've handled math classes just fine, to put their programming brain on, programming thinking cap on, because to switch from that math mode to like computing or computer science mode is not easy. Okay, so now what I can do is, now that these functions are in place, I'll make sure this, messed up. Okay. Oh, I see why. In fact, when I did this last night, I ran into the same problem. B is not defined at this point. So what I'm going to do is I'm going to pre-allocate it to make a 0 vector the same size as C, because I know I'm going to have the same size. So that's one wrinkle, unfortunately. And now, dang it. I knew embarrassment had to come at some point. Okay, so that has the correct index exceeds matrix dimension. So there's an index here that's bad. Okay. So C has a correct length. Okay. Okay, that's extra weird. So, actually, I want to take a look at this anyway. I know I'm just about out of time. Okay. Oh, I have a wrong divided differences. That's one thing I need to fix. All right, that explains that mystery, but it doesn't solve the whole thing. All right, C is a vector of length 3, and that's what it's supposed to be. And then, I'm going to be so pissed if this ends up not working and class has to end. And I know what's going to happen. As soon as you all walk out of here, I'm going to see what the problem is. Okay. So, yes?
Is the second for loop supposed to end it too? Or is that...
Yes, it is. Yeah, it's supposed to have one iteration less. But the problem, the error is actually happening up here. And if I print out B also, B has the correct length. And N is 2, so that's correct also. And the thing is, I can't tell which index is... Oh!
You have to declare X first.
No, I know. I found the problem. Okay. XC, not X. X is a scalar. XC is a vector. I was referring to the wrong thing. Okay. All right. So now I need to print this out. That's the power form. Okay. So now this is correct. It works. Thank God. All right, and I'm done. Okay, so I'll post both versions of the code. For the very last point, I will take 10 seconds, I swear to God. Here I'm calling nested mult 2, but twice. But it's for second degree interpolation. If I want to do general nth degree interpolation, what should I do to these two statements? Yes, put them in a for loop that runs n times. Very good, now you can go.